So, all right, good morning once again, students, and especially to our professor for this morning, Dr. Raymond Indangan. And our topic for today is all about the test for non-absolute convergence. So, let's start with the alternating series. So, the alternating series is the most familiar test for non-absolute convergence series. The one is made, so it is applicable to series that are alternating in the following sense. So let's start with the definition. So 9.3.1 definition, a sequence x equals to x sub n of non-zero numbers is said to be alternating if the terms negative 1 raised to n plus 1 times x sub n, where n is an element of natural number, are all positive or all negative real numbers. If the x equals to x sub n is alternating, we say that the series sigma x sub n generates is an alternating series. In this case of an alternating series, it is useful to set x sub n equals to negative 1 raised to n plus 1 times z sub n, or x sub n equals to negative 1 raised to n times z sub n, where z sub n is greater than 0 for all n is an element of natural number. And we have 9.3.2 alternating series test. Let z equal to z sub n be a decreasing sequence of strictly positive numbers with the limit of z sub n equals to 0, then the alternating series sigma negative 1 raised to n plus 1 times z sub n is convergent. Proof: since we have a sub 2n equals to the quantity of z sub 1 minus z sub 2 plus the quantity of z sub 3 minus z sub 4 plus plus the quantity of z sub 2n minus 1 minus z sub 2n, and since z sub k minus z sub k plus 1 is greater than or equal to 0, it follows that the subsequence of s sub 2n of partial sum is increasing. Then we have a sub 2n equals z sub 1 minus the quantity of z sub 2 minus z sub 3 minus minus the quantity of z sub 2n minus 2 minus z sub 2n minus 1 minus z sub 2n. And it follows that a sub 2n is lesser than or equal to z sub 1 for all n is an element of natural number. It follows from the monotone convergence. Theorem 3.3.2, assuming that we already understand monotone convergence. So, therefore, that the subsequence of s sub 2n converges to some number s is an element of real numbers. So, we now show that the entire sequence s sub n converges to s. Indeed, if epsilon is greater than 0, let k be such that if n is greater than or equal to k, then the absolute value of s sub 2n minus s is lesser than or equal to 1/2 epsilon. And the absolute value of z sub 2n plus 1 is lesser than or equal to 1/2 epsilon. It follows that if n is greater than or equal to k, then we can solve this. So the absolute value of s sub 2n plus 1 minus s. So we further expand. So we have the absolute value of s sub 2n plus z sub 2n plus 1 minus s. And then lesser than or equal to s sub 2n minus s, lesser than or equal to the absolute value of s sub 2n minus s plus the absolute value of z sub 2n plus 1 is lesser than or equal to 1/2 epsilon plus 1/2 epsilon, and then we come up with epsilon. So therefore, every partial sum of an odd number of terms is also within epsilon of s if n is large enough. Since epsilon is greater than 0 is arbitrary, so the convergence of s sub n and hence of sigma negative 1 raised to n plus 1 times z sub n is established. And we have 9.3.5 Abel's test. We have here f x equals to x sub n is convergent monotone sequence and the series sigma y sub n is convergent, then the series sigma x sub n y sub n is also convergent. Proof: if x sub n is decreasing with limit x, let u sub n equal to x sub n minus x, where n is an element of natural number, so that u sub n decreases to 0. Then x sub n equals to x plus u sub n, whence x sub n, y sub n equals xy sub n plus u n sub y sub n. It follows from the Dirichlet test 9.3.4 that sigma u sub n y sub n is convergent, and since sigma x y sub n converges because of the assumed convergence of the series sigma y sub n, we conclude that sigma x sub n y sub n is convergent. If x sub n is increasing with the limit x, let v sub n equal to x minus x sub n, where n is an element of natural number, so that v sub n decreases to 0. Here, x sub n equals to x minus v sub n, whence x sub n y sub n equals to x y sub n minus v sub n y sub n, and the argument proceeds as before. And that's all for this morning.